the initial kinetic energy is greater than the final kinetic energy, but they don't stick. Don't stick together. In naming convention number 1, this is known as an inelastic collision. Naming convention number 2, this is known as an elastic collision. And thus you can start to see that there's potential conflict here. If the initial kinetic energy is greater than the final kinetic energy, in other words, there's a loss of kinetic energy, but they do stick together. Naming convention number 1, this is known as perfectly inelastic. Naming convention number 2, this is known as inelastic. The idea of this convention number 2 is that if I drop an object and it bounces, there's some elasticity there. And if it just, I drop it and just sticks to the floor, then obviously there's no elasticity, so it's inelastic. Naming convention number 1 is looking more from energy point of view. Elastic, from their point of view, is I drop a tennis ball, it bounces up to the exact same height as it did before. And if there's any loss of kinetic energy, then obviously we're dealing with less than perfect. And so therefore there's some loss of elasticity or some inelasticity.
Wait, so for the second one, are you just saying like these two, naming convention 1 and convention 2, are those both from different textbooks?
Yes.
Oh, okay, got it.
And different websites.
So they just define elasticity differently?
Yes.
Okay, that's a little, so if you ask us like, is this elastic or inelastic, and it's like one of these, we could say either one, and you would be like, yeah.
Well, to eliminate that, and by the way, this is now wrong because I just raised the definition of D since there's no D defined. So let me rewrite that up there. So D.
Can we use any symbol if
As long as,
Huh?
as long as it's not being used.
Okay.
Yes, and you define it.
Because
Okay.
Dr. Fox said so. What was it? E, D, F, S, S.
What I will be using, to avoid the confusion of, what does he mean by elastic or inelastic, I use perfectly elastic and perfectly inelastic. So perfectly elastic, kinetic energy is conserved. Inelastic, they stick together. I just picked the two extremes. And that leaves, what do I use for the middle? Suppose there's loss of kinetic energy, but they don't stick together. I had a student suggest this a couple years ago, and I liked it. Imperfect.
Just imperfect?
Yep, just imperfect. Now, there is one other category that sometimes shows up. A textbook occasionally will do it just to see if you're paying attention, and I sometimes will do it sometimes to see if you're paying attention, and sometimes because I made a mistake. The initial kinetic energy is less than the final kinetic energy in the absence of explosions. No explosions. So I set up this problem. If I picked, say, the 5 kilogram mass was bounced back at 10 meters per second, our total kinetic energy in the end would have been greater than what we started with. These two conventions call this impossible.
Let's say.
I call it Flubber-esque.
From the movie Flubber?
Yeah.
Actually, from the movie The Absent-Minded Professor, but sure,
Huh.
from the movie Flubber if you want.
So there's like no scenario where the final kinetic energy will be greater than the initial energy.
There would have to be a source of energy that would cause that. That's I said no explosions. If I throw an object in the air and it explodes into pieces,
Something had to cause that, yeah.
yeah, that basically is the reverse of a perfectly inelastic, where If the three pieces came together and stuck perfectly inelastic, if I had an explosion there and suddenly it breaks into three pieces, it's just the reverse of this. But I've introduced another, I've introduced energy into the system in that case.
So there's no natural known system where the kinetic kinetic energy will be greater when it's initial, greater in final than it is in initial, other than explosions.
In a closed system,
Right.
Okay,
right? So in an open system, you could.
okay,
So if Flubber actually existed,
yeah,
if it were possible, that means I could take this object, bounce it, and it would bounce higher than it started with. And then keep bouncing more and more.
okay,
It'd be free energy, or it'd have to take energy from the ground somehow.
yeah,
Now, I'm willing to bet that there's some quantum mechanics way that it is statistically possible, but very improbable.
yeah, okay,
However, we're doing classical physics right now.
okay.
All right, I will tell you that on the last test, so not the one on Wednesday, the one after that, there will be a problem where you are gonna do a one-dimensional perfectly elastic collision, and there will be another problem where you'll do a one-dimensional perfectly inelastic collision. I will guarantee the last test will have one of each of those two types. Lisa?
So we have a test on Wednesday and only one more after that?
Remember the multiple choice test you did the first day?
Yeah.
Yeah, you'll get to do that again. The second time was for a grade.
So we're gonna have, that's 4 tests?
Before test grades.
Okay. And will that last test be like a kind of like a final exam kind of?
Not officially accumulative or cumulative. It will officially be from chapter 7 onwards. But,
So basically just like a 4 test, but
yeah.
that's multiple choice. So it's a 4 test, but the format is in multiple choice.
No, the multiple choice test is separate, is a different test than, the last test will be similar to what you did on the first test and what you'll do on the second test. But there's also a multiple choice test, the one that you did the first day. We'll have covered all the material.
Oh, okay. I see.
All right. A 3-kilogram mass traveling to the right at 4 meters per second. It collides with a 6-kilogram mass that was traveling right, now let's do head on, left at 2 meters per second. If the collision was perfectly inelastic, what is the final velocity? Sort of a typical wording. You can embellish it with a 3 megagram rocket was heading straight towards Earth. It's still far enough away for the gravitational influence not to be significant. Heading straight towards it was a 6 megagram missile heading straight towards it. when they collide. Then I'm throwing something that the missile doesn't fire, doesn't explode, so therefore keeping that part of it out. Anyway, that's the essence of what we're working with here. So let's, my first recommendation is draw the picture. 3 going to the right at 4 meters per second. 6 going to the left at 2 meters per second.
Question, does the fact that, like, okay, 3 is half of 6 and 4 is half of 2,
Oh,
does that have to do
Just-
anything with, like, does that help us at all? Like, to determine what the final velocity is, or was that just a,
that was not by design, I mean, it's not like, I did not think about that ahead of time. So,
So is the final velocity just 0?
yeah, final velocity would be 0. That's a boring problem.
oh, wait, hang on,
Yeah.
because,
They have
Oh.
the same momentum coming at each other, so there's no,
What, the wording?
well, one of them's negative, one of them's positive, so they even out to 0.
oh, yeah.
Yeah, that,
Okay.
so let's change the problem.
Well, it's cause they stick together, right?
Yes.
Stick to, okay,
Oh,
wait, so
God.
every time they stick together, is it always gonna be 0?
No,
Why not?
but the first example I did wasn't 0.
Oh, yeah, cause they could like, it could still move.
They have the same magnitude of their momentum.
Mhm.
Or if total momentum is 0 beforehand, then a perfectly inelastic collision will be 0 afterwards.
Right.
And that actually, when we solve the perfectly elastic collision, that actually is one of the 3 techniques to solve it, to take that into account. However, we're not there yet.
How can there be a collision if initial momentum is equal to 0?
Total is 0. We're not saying that the individual parts are 0,
Okay.
we're just saying that the total is 0.
Okay.
All right. So questions about why they would hit and just stop?
Wait, don't they not stop? They bounce off.
No, they stick together.
Perfectly inelastic. You misread it.
Oh, yeah.
The perfectly inelastic, they stick, and in this case, they will stop. Maximum kinetic energy loss, because, well, kinetic energy went down to 0. All right, so let's change this to 5 meters per second. All right, so now
Shooting that way, yeah.
we need to establish the positive direction. Okay, it's all Brooks' finger first.
Okay, sure. So, yeah, it's gonna be negative.
So my total momentum, 12 plus negative 30. So there. Now occasionally I have students who look at this and they keep wanting to bring the weight of each object into play. There's nothing in here to indicate that weight should be brought into play. I've not put this near a planet. For these type collisions, just assume, if you need to, it's on a flat surface and the flat frictionless surface heading towards each other, if that makes it more real for you. So what's my final total momentum?
Negative 18.
Yep. And that's gonna be equal to final mass times final velocity. Now, there is a clue here for you get into a test and suddenly your mind blanks, and so if you happen to be thinking in a certain way, I asked what is the final velocity? These are singular, so that tells you, should be telling you that I'm looking for one answer. To sort of go along with perfectly inelastic.
Can we add the 2 masses together to find the velocity? Like, it says like mass final, so would you add together 6 and 3?
Yes.
And solve for velocity?
Yes, there are 2 ways of doing it. That's the way I typically do it right there. So I have negative 18 is equal to 9 final velocity. Wow, another integer. It's nice when it works out that way.
Negative meters per second.
Yeah. So after the collision, they will both be heading to the left at 2 meters per second. The other way of doing it is you don't consider them, you just consider them two masses that are traveling together. And so you'd have negative 18 is equal to 3 final velocity plus 6 final velocity. You do have to recognize that their velocities afterwards are the same because they're sticking together. But you could treat it this way, in which case you add common terms and you're back here again. What is it?
So where did we get 9 from?
The fact that it's perfectly inelastic, that is the key terminology right there, means that they're gonna stick together. So I have these two masses, I have the 3 and the 6 kilogram masses, they stick, so now there are one 9 kilogram mass.
Alright, and, what was I saying? Oh yeah, so if negative 18 is the final momentum,
Yes?
then how did we do the initial momentum?
Initial momentum, you find the momentum of each one and add them together. So this one is mass times velocity, so that's 12. So basically 3 times 4 got us to 12. And over here, the mass is 6 kilograms times the velocity of negative 5 meters per second. And that got us to negative 30.
So the initial and final are the same.
Total, the totals are the same, yes.
Okay.
That's the idea of conservation of momentum. Whenever I start, so my total beginning is the same as my total after.
So our, what's it called? The impulse would be 0 since it's,
Impulse on the total system would be 0, impulse on each individual mass is not. Because this starts out with 12 Descartes, so it starts out with 12 Descartes. It ends up with 3 times negative 2 goes to negative 6, so this goes from 12, if I can make it 12 nowadays, 12 Descartes down to negative 6 Descartes. And so the impulse on this one was negative 18. The impulse, just coincidence that it matches this. This 6 kilogram starts out at negative 30 Descartes, and it will go to, afterwards, it's going at negative 2 meters per second, so it goes to negative 12 Descartes. So the impulse on this one was positive 18.
Oh, you just have to like calculate the change in the momentum for the impulse?
Yep.
Okay, gotcha.
Because that's what we have.
Yeah.
Because the force is not constant, so force times time, I could do an average force times time. Or change it up and go, what is the impulse on the 6 kilogram mass? Suppose that it went from its initial speed to its final speed in a half a second. What was the average force? In which case, you would then set that impulse to average force times time.
Also, okay, are all of these, like, the naming conventions for all of the kinetic energies, this is all based on the assumption that momentum's conserved?
Yes,
Okay.
yes. So I guess I should parenthetically write closed systems.
Do we have naming conventions for open systems?
Typically not.
Are we even gonna deal with open systems?
Yeah, I mean, in some sense, what is the initial, if I'm asking for the impulse on the 3 kilogram mass, I'm sort of dealing with an open system there.
Okay.
Open system problems typically are simpler, because you have to you're given more information.
Okay.
Unless you hate information, then I guess it's more complicated.
Yeah.
Brooke, you were asking something?
It was just like talking about open systems, but it makes sense.
All right, any questions on this before I change the problem slightly? Of course.
I do have a feeling this is gonna get a lot harder for no reasonable, for no reason.
Don't jinx it.
We've now made it a perfectly elastic collision. So I have that 3 again, just drawing the picture up again, because I erased it for some unknown reason. So that was 4 meters per second. I have the 6 kilogram mass going to the left, 5 meters per second. My initial momentum was negative 18 Descartes. Perfectly elastic collision. Oh, this needs to change also. What are the final velocities? So I'm expecting 2 answers here because you need to find the final velocity of each mass. So I at least want to set up the equations. Now I'll write out the equation and I'll do my substitution. So we end up with negative 18 is equal to 3v 3 final plus 6v 6 final, or 1 and 2, or A and B, however you want to designate the 2 different ones. That's my conservation of momentum equation right there. But because it's perfectly elastic, kinetic energy is conserved. And so I have 1/2 3 times 4 squared
It's 20.
plus 24 plus 1/2 times 6 times 5 squared
25 times 3 is 75.
equals 1/2 3 v3 final squared plus 1/2 times 6 times v6 final squared. So that is 99 equals 1.5 v3f squared plus 3 v6f squared.
So we're solving for the velocity, right?
Well, yes, finding the velocities.
Okay.
Couple things to point out. 1, 2 equations, 2 unknowns, it's an algebra problem now. 2, you will be using the quadratic formula. 3, when we get our 2 answers for each of them, because remember it's quadratic, so you'll end up with 2 answers, we will know immediately if we've made a mistake.